Assalamualaikum everyone, hope you're doing well. Ariba this side. So today I'll be walking you through my AI project where I implemented a Tic-Tac-Toe game using the Minimax algorithm and its optimized version with alpha beta pruning. This project explores how game playing AI make decisions and compares the performance of both algorithms. Okay, so what is Tic-Tac-Toe? Tic-Tac-Toe is a classic two-player game played on a 3x3 grid. So players take turns making either, for example, cross or a zero, and the first to align three marks horizontally, vertically, or diagonally wins. Although simply, it's widely used to teach decision-making algorithms in AI due to its manageable complexity and clear win-loss states, because it's too easy to understand as a beginner that how the decision making algorithms works. Okay, let's talk about the Minimax algorithm. So Minimax is a recursive algorithm used in two-player turn-based games. It simulates all possible moves until the game ends. So one player aims to maximize their score and the other tries to minimize it. The AI assumes the opponent will also play optimally and chooses moves that give the best guaranteed outcome. Okay, what is alpha beta pruning? So alpha beta pruning is an optimization applied to min-max. So it helps the algorithm run faster by ignoring parts of the game tree that don't need to be explored. Alpha tracks the best score the maximizer can guarantee, while beta tracks the best for the minimizer. When beta becomes less than or equal to alpha, we cut off that branch, saving computation time. Okay, so code overview of a game class. So the Tic-Tac-Toe class contains all the game logic. It manages the board, track movers, checks for winners, and handles undo operations. The board is a simple list of 9 elements representing 9 squares. And we have make move function as well that place a letter and check winner evaluates the rows, columns, and diagonals. Okay. Now let's talk about the min-max function. So this function recursively simulates each possible move. So whenever it reaches a terminal state like a win, lose, or draw, it returns a score, right? Now the AI playing an, for example, X maximizes the score and the human playing an O minimizes it. So we also count how many nodes are evaluated to compare the performance. Okay. Now code overview of alpha beta pruning. So the optimized version of min-max introduced two variables alpha and beta. They help track the best guaranteed outcome for each player. If during recursion we realize that a move cannot yield, for example, a better result that what we already have, we prune that part of the tree. So this makes the algorithm significantly faster. Okay, let's talk about the testing setups. To compare the both algorithms, I created 3 test scenarios: an empty board, a mid-game state, and a nearly complete end-game state. The test performance function on both algorithms records the time taken and nodes evaluated. This helps visualize how effective alpha beta pruning really is. Okay, so play demo function. So I also built a function called play demo to let user play interactively from the command line. The user plays as 0, for example, and the AI plays as X. So the board is printing after every turn and the AI calculates the best move using the min-max algorithm with pruning. This demonstrates the AI in action. Okay, so to summarize, the min-max algorithm guarantees the optimal play for the AI. Alpha beta pruning drastically improves the efficiency, especially at the start of the game. Tic-Tac-Toe is an ideal project like to practice game in AI, and the structure can be extended to more complex game like chess. So thank you so much for listening to my presentation. Now we will be also discussing the output of this project. I'll be running this project on an online compiler, and we'll be discussing inshallah ta'ala the project demonstration also, like how the things are going on by playing the game, so for a better understanding. Okay, so now let's discuss the output. So I already played this game, so let's analyze what's going on in the output. So first of all, we have empty board test case. So with an empty board, the number of possible move sequence is at its maximum. So the standard maximum minimax took around 1.87 seconds and evaluated over 46,500 nodes. In contrast, alpha beta pruning completed the same task in just 0.07 seconds and evaluating over 17,757 nodes. Okay, so this shows the 96% improvement in both the time and nodes evaluated, making alpha beta significantly more efficient when the game tree is largest. Okay, let's discuss the mid-game test case. So the mid-game test case where fewer moves are left, so standard min-max still took about 2.3 milliseconds and evaluated the 70 through 3 nodes. Alpha beta pruning reduced this to just zero point 0.6 seconds and 163 nodes, offering a 75% speed up and 77% reduction in computations. Okay, so now let's talk about the end game test case. So by the end game, most of the board is filled, so the game tree is smaller. So the standard min-max took 0.6 seconds. Okay, and the beta took 0.4 milliseconds with a smaller yet still meaningful 36% improvement and 39% fewer nodes evaluated. Okay, so now we have actually played the game. Okay, so first of all the board was showing, and then it asked me like select the move. I chose the position 2. Then AI was thinking like he chose the position 0th. Then my turn, I chose 4, then similarly 6, and I won the game. So then it is also printing the things for the playing. Okay, so let's discuss the gameplay demo as well, right? So the output shows an actual game between the AI and human players, right? So the board positions are numbered from 0 to 8. The player chooses position 2, placing 0. The AI responds with a move 0, choosing X after evaluating 8445 nodes in 0.04 seconds, right? So, okay. Now the game continues with the player choosing enter center, for example 4, right? And the AI responds with a move 3. Alright. Now as the game results, for example now my turn, I chose the possession 6th, right? So finally the player wins by completing a diagonal with a move 2, 4 and 6. So the AI tried to counter but couldn't block the winning move in time. This interactive demo shows that even though the AI uses optimization, a skilled player can still win. Okay, so that's all for this project. I hope you like it, and we have also discussed that how alpha beta pruning helps, and we also have discussed this in the form of the output as well. Thank you so much.